I think one of the more helpful applications of Avogadro's law is in the context of stoichiometry problems. So let's have a look at this one here. What volume of ozone would result when 27 liters of diatomic oxygen reacts at constant temperature and pressure? So notice that last little bit here. When we're at constant temperature and pressure, Avogadro's law applies. And what that means is we're going to have a different volume when we have a different number of moles. There is a directly proportional relationship between those two variables. Okay, so more moles, more volume, less moles, less volume. So let's look at what's actually happening in this chemical reaction on the molecule level. 3 diatomic molecules of oxygen join up to make 2 molecules of ozone. And at first you might think, well, how is that going to impact the volume? You still have the same number of atoms here. Okay, well, Avogadro's insight was the fact that it's not really the number of atoms that matters so much, it's the number of particles. These particles are all really, really, really tiny in comparison to the volume of the container. And the amount of space that these particles actually take up is so small that we just basically say they're kind of like the same size and relative to the container, and so that they're in. And so here we have 3 particles that are bouncing around rather than 2 particles bouncing around. And those 3 particles are going to cause more collisions with the container, and so the volume is larger because of the result of all those collisions. At any rate, that was Avogadro's hypothesis, and a lot of people, kind of disputed it, but it turned out to be a very, very helpful way of looking at things. And so here we can see that 3 particles is turning into 2 particles because of how the atoms are arranged. And so let's try to apply Avogadro's law to this problem. Avogadro's law tells us that the ratio of volume and moles is constant. Okay, and so what do we actually know numerically from this problem? We know that there's 27 liters, but we don't know the new volume that results. That's ultimately what we're trying to figure out. That's the big question. And we don't even really know the numbers of moles, if you think about it. In this particular sample of gas, there's a lot more, well, there could be. We just don't know the number of particles here. This is the coefficient in the reaction, but we don't necessarily have 3 moles of oxygen here. We really don't even know how many moles of oxygen we have. But we do know something important. As the reaction progresses, we're going to have less particles. And in fact, we're going to end up with 2/3 the particles at the end. Okay, so 2/3 the particles means we're going to have 2/3 the volume. Okay, so let's say if our original number of moles was here, right? We don't even know what that is, but if we have 2/3 of that, that'd be somewhere like, that's 1/3, 2/3. 2/3 the number of particles, we're going to have 2/3 the volume. Okay, so what's 2/3? So we can basically still use these coefficients, is what I'm saying, even though we don't know the real number of moles. So we plug in to Avogadro's law, and we can say our final volume is going to be N2 over N1 times V1. And even though we don't know the number of particles, we know that this ratio is going to be 2/3. So 2/3 times 27 liters is 18 liters. Okay. This leads to an important result. Up until now, to do stoichiometry, I've emphasized to you guys, you need to know moles. You need to know the numbers of moles, and we don't know the number of moles here. However, if you're at constant temperature and pressure, there's a neat shortcut, and it's because of Avogadros' law. The coefficients also represent the relative volumes. So at constant temperature and pressure, the coefficients represent the relative numbers of moles and volume of gases, as long as you're dealing with gases. Okay, so let's look at one more example here. Let's say we have the combustion of hydrogen yielding water vapor. And let's say this is happening at a really, really high temperature, so the water just stays in the gaseous state. What volume of oxygen will react exactly with 5.8 liters of hydrogen at constant temperature and pressure? And what volume of water vapor will result? Okay, so we have 5.8 liters of hydrogen. We don't know how many moles of hydrogen are there, but it's at constant temperature and pressure, so Avogadros' law applies. In other words, the coefficients represent the relative numbers of moles, but also the relative volumes. So we have a 2-to-1 ratio for the moles, which means a 2-to-1 ratio of the volumes. So basically, however much volume of hydrogen we have, we need half of that volume of oxygen. So 5.8 liters of hydrogen, we can use the coefficients on the equation as relative volumes. So every time 2 liters of hydrogen react, we need 1 liter of oxygen. So that is 1/2 the volume of hydrogen. So that is 2.9 liters of oxygen, half of 5.8 to 2.9. And we can also do another volume to volume ratio. Every time 2 liters of hydrogen react, we form 2 liters of water vapor. So we would form 5.8 liters of water vapor. Those would be our 2 answers. Okay, so these coefficients also represent the relative volumes when you're at constant temperature and pressure.